Hello and welcome to G Fun Facts Online, the place where we explore the amazing and the mind-boggling. Today we're diving deep into the world of supermaterials, and trust me, this one's a game changer. Ever heard of forces so weak? Scientists thought they were practically useless for building anything strong? Well, get ready to have your assumptions shattered, because we're talking about van der Waals frameworks, or as I like to call them, WaaFs. Now, van der Waals forces, stick with me here, are these gentle, fleeting attractions between molecules. Think of them like those weak, reusable sticky notes. For a long time, the scientific world believed these forces were just too flimsy to create stable, open structures. Materials with lots of tiny holes and tunnels, which are super useful. But then, some ingenious researchers, particularly from Kyoto University, decided to challenge that notion. And boy, did they succeed. They pioneered the world's first three-dimensional van der Waals open frameworks. Imagine building with Legos, but your Legos are these tiny, complex structures called metal organic polyhedra, or MAPs, larger than 2 nanometers. These MOPs cleverly arrange themselves into sparse, diamond-like networks. The secret to their strength? These MOPs have well-defined flat faces, like facets on a jewel. This design dramatically increases the contact area between them. It's like pressing two large flat surfaces together instead of just two tiny points. The stickiness multiplies. This results in van der Waals interaction energies that are surprisingly powerful, sometimes over 400 kilojoules per mole. To put that in perspective, anything over 200 kilojoules mole is usually considered strong bond territory, like the stuff used to make other robust materials called MOFs and COFs. So these supposedly weak forces are adding up to create something incredibly sturdy. So what makes these WaaFs so special? Well, for starters, they boast incredibly high porosity. We're talking specific surface areas that can exceed 2,000 square meters per gram. That's like unfolding a football field's worth of surface area from just a tiny pinch of material. This massive internal surface is perfect for grabbing and storing things. Then there's their thermal stability. These WaaFs can keep their cool and their structure, even at temperatures as high as 320 degrees Celsius or 593 Kelvin. That's hotter than your oven on full blast. This resilience opens up a whole new world of applications in high-temperature processes. But here's a really neat trick. WaaFs can be disassembled and reassembled in solution. Think about that. You can break them down and build them back up. This is fantastic for scaling up production and for recycling the materials, making the whole process much more sustainable. Plus, their porosity can be tuned. Scientists can essentially design the size and distribution of the pores, and these materials are chemically stable. Talk about custom-made. With properties like these, the potential applications are thrilling. Imagine WaaFs being used for gas storage, packing hydrogen or methane fuel efficiently, or for separating gas mixtures, like capturing carbon dioxide from factory emissions to help fight climate change. They could act as tiny chemical factories, with their porous structures hosting catalysts to speed up reactions. Picture them harvesting water vapor from the air, even in arid deserts, providing a new source of fresh water. Or they could be used in molecular sensing, sniffing out specific molecules for medical diagnostics or environmental monitoring. This development of WaaFs is a huge deal. It's a paradigm shift in how scientists think about these non-covalent interactions. Those van der Waals forces, once dismissed as too weak and directionless for building permanent, porous solids, have now taken center stage. By cleverly designing structures that maximize intermolecular contact, we're talking over 200 atoms involved in the interaction. These weak forces combine to create strong, reliable bonds that can support robust frameworks. This breakthrough isn't just cool science. It redefines the rulebook for designing porous materials. The scalability and recyclability WaaFs offer are particularly exciting, tackling some of the biggest hurdles in getting advanced materials out of the lab and into the real world. As research powers on, van der Waals frameworks are truly poised to offer innovative solutions for some of our planet's biggest challenges, from clean energy to environmental cleanup. So the next time you hear about something being weak, remember the story of WaaFs, where the collective power of the gentle giants of the molecular world is building the materials of the future. Thanks for tuning in to G Fun Facts Online. Join us next time for more fascinating insights. Stay curious, everyone.